So today we're going to learn about inverse variation. It is the opposite of direct variation, which we learned earlier in the year. Direct variation was y equals k times x. What this said was as one thing goes up, so as x goes up, y goes up. Now we're going to learn about inverse variation, which states that as x goes up, y goes down. So you have two things that will work in opposite order. So as x goes up, y goes down. As x starts to go down, y would go up. Inverse variation will always be in the form y equals k divided by x. K is what we call the constant of variation. X is always in the denominator. This is just a very much simpler form of a rational function, where p of x, the numerator, is just k. And q of x, the denominator, is just x. K has a degree of 0. X has a degree of 1. And so what we'll look at is we'll look at some examples. We'll compare what happens with our asymptotes here, because we still get discontinuities. Remember, the title of our chapter is Rational Functions. We get discontinuities when the denominator, or q of x, is equal to 0. When q of x is equal to 0, we have a function that is undefined. We will eventually get into translations of inverse variation. So inverse variation just has k and x, but the translation has addition and subtraction. Remember, a parent function, which this is, always gives us our shape. A translation will move our shape. It'll take that shape and it'll slide it up, around, down, and over. So if I look at an example here, I have y equals 5 over x. What I notice is that I'll have a k equals 5. There is always a value for k. Over here, I have x, and it's just by itself. So the first thing you're going to be asked to do is sketch a graph of this. The easiest way to sketch any graph is going to be to create a table. Or maybe not the easiest, but the most basic way. And so what we want to do, guys, is create many points instead of just 1 or 2. 1 or 2 gives us a good picture for a line, but not for something that's going to have 2 branches and they're going to be curving. So I put all these numbers in for x. I'm going to start with the easiest one. The easiest one is 0, because 5 divided by 0 will always be undefined. Over here, if I put in 1, 5 divided by 1 is 5. 5 divided by 2 is 2.5. 5 divided by 3 is 1.6 repeating, and 5 divided by 4 is 1.25. And so here's where we get our pattern of inverse variation. As x goes from 1 to 2 to 3 to 4, as in going up, y is going from 5 to 2.5 to 1.6 to 1.2, going down. this looks like a lot of math problems. Fill in these boxes by simply taking these numbers and taking their opposites. And so now I've created quite a few points. I draw my graph. And I start to plot my points. Before I plot my points though, I can put in my vertical asymptote and my horizontal asymptote. If I look at the translation up here, I notice that x equals the value of b will be the vertical asymptote. In this particular case, what is the only number that I'm adding underneath the division sign? And it is 0. And so what I know is that my my vertical asymptote is right at 0. So I use a dashed line right next to the axis so I can see it, and I label it as x equals 0. Two ways to figure out your horizontal asymptote. We could look at the degrees. We did have a way to determine it by that. Or we can just look at whatever is out here. And that number is also 0. And so you have a vertical asymptote at y equals 0. Note, this will only work if this degree is 0 and this degree is 1. It won't work if you have quadratics in the denominator. Now I know I have these asymptotes, places where my function will approach but never touch. So no line I draw on this graph should cross these dashed green lines. And I start to plot these points and I say, okay, at -4, I'm here, 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 and here. It is very important to note, guys, this does not have to be entirely accurate. You need to make it as proportional as you can. So my -5 was about twice as far down as my -2.5. I get the same sort of thing up here. When I put in 1, I get 5. And that becomes my graph. That is how you would graph by hand inverse variation. Now, as we scroll over, let's look here at our calculator for a second. If you're using a calculator, this can actually be very easy. All you would have to do is hit your y equals button, clear out all of your equations, put in 5 divided by x, and hit graph. Hit zoom fit and it'll show you the picture. You could sketch the picture just as I did. Now, in order to get the table of values that you need, all you would have to do is hit second, table, and then fill out all your values. And it's just that simple. Okay? So now let's look at something that is translated over this way. Excuse me. Alright, so now here we see a function. This is inverse variation, but it is translated. If I wanted to write the parent function, I am going to take out all addition and subtraction. So the parent function here would simply be y equals 2 over x. Remember, the multiplication and division will give us the shape, and the addition and subtraction will take that shape and slide it over and down, over and up, this way or this way. So, I graph based on this because it'll be nice and easy. Okay? But even before I create my table of values, I'm going to come over here and I'm going to put my asymptotes. Remember, asymptotes are types of discontinuities. Discontinuities are places where our function is undefined. Okay? You have a vertical asymptote and a horizontal asymptote. From our last example, we know that the horizontal asymptote will always be this number right here. And horizontal will always be y equals a number. So y equals -1 becomes my horizontal asymptote. What I notice about my vertical asymptote is that it is the opposite of this number here, and it's x equals -6. So now I go to -6, and I'm going to put a vertical asymptote. Remember, those are lines our graph approaches but never touches. So whatever I put on this graph will not cross this red asymptote, and it will not ever cross this green asymptote. If I were to do this by hand, I would look at the parent function first. I would create my chart, and I like to use -4 to 4. I think it gives you a pretty good picture. As I start to put in these numbers, some of them are nice and easy. 2 divided by 4 is 1/2. 2 divided by 3 is 2/3, which is 0.6 repeating. 2 divided by 2 is 1. 2 divided by 1 is 2. 0 is our undefined. And then we reflect all our values. Just like that. Now, I could plot all those points. As I come through, I have 1, 2. Right about there. And 2, 1. But this is a translation. What it means is that every one of these points is going to go 6 this way, and 1 down. So that this point, if I went from 1, 2, and I subtracted 6 from the x, it would be -5, and I subtracted 1 from the 2, it would be -5, 1. This point, that was 2, 1, if I subtract 6 from that, becomes -4, 0. And so on and so forth. And it'll work for every single point. They're all going to move 6 over and 1 down. What we notice about our asymptotes is that the asymptote went 6 this way, and the horizontal asymptote went 1 down. The entire graph and every point on it will follow that same pattern, so that your final picture will look like this, where we notice that we have 2 distinct branches, but they are no longer limited to the first and third quadrants, but they are now in the upper right of our 2 asymptotes and the lower left of our 2 asymptotes. So positionally they look the same, but this one actually crosses through every quadrant except the first. This graph right here, with the asymptotes labeled, with a chart right here, and with the branches in the correct areas. Notice, it doesn't have to be a specific point. You don't have to have 20 points labeled. I see all your points up here. This graph right here is good enough. Now, you can also do this on your TI-84 or 83, 82, whichever type you have. If you wanted to do this in your calculator, the pieces that you would need to remember are a few parentheses. What I want to do is 2 divided by x plus 6, so I put parentheses around there. If I put parentheses around this, it's going to do x plus 6 first, then it'll do 2 divided by that, and then it'll do minus 1. If you put this entire thing in your calculator, this is the picture that you would get. You would then go to your table, and you would look at this, and you would look for about 8 values, except our values shouldn't be 4 to the left of 0 and 4 to the right of 0. It should be 4 to the left of the vertical asymptote and 4 to the right of the vertical asymptote. So I put my vertical asymptote in the middle. So I've got negative 6, 2, 3, 4, right here. That is where this function is undefined. If I look at the table in my calculator, it will tell me what is negative 7, negative 8, negative 9, and negative 10, negative 5, negative 4, negative 3, and negative 2. Notice, this is your asymptote, the middle value, the undefined value. Then, well, we already did our negative 5, that was 1, this was 0, and all I would do is take my y value and subtract 1 because of this each time. So 0.6 minus 1 is negative 0.3. If you're using your calculator, it's going to do all this for you. This is negative 1/2. Over here, we just now reflect this. You take these, don't reflect it, take these, and you have to subtract 1. That would be negative 3. This would be negative 2. This would be negative 1.6. And this would be negative 1 and 1/2. Notice, if I'm doing it by hand, this is much easier to calculate. If I'm doing it on a calculator, my calculator does all this for me. And that's actually kind of nice. Because by hand, I've got to do all the points using the parent function. This is the actual or translated function. We go from there. Alright, so one more example as a comparison point. Okay, so if I want to compare 5 over x to 10 over x, this is interesting because it tells us what to do, or what our branches tend to do. If you have a coordinate plane, and there is no addition or subtraction in either of these, we automatically know that our asymptotes are y equals 0 on the x-axis, and x equals 0 here. So what I do is I plug both of these in my calculator. I put this in for y1, and I put this in for y2. In my calculator, the first two branches will always be whatever y1 is. What you find is that this, and let me do that in blue so it matches our question here. This gives me a curve like that. Two branches never crossing the asymptote, because the asymptote is where the function is undefined, okay, in part when the denominator equals 0. When it shows me y2, it's going to show me a curve like this. This is y equals 10 over x. And so, when I ask you to compare things, I'm asking you to tell me what are the similarities and what are the differences. My conclusion here in a comparison would be something like this. The graphs appear in the same quadrants, quadrant 1, quadrant 3, but the y equals 10 over x is further from the intersection of the two asymptotes. The intersection of the two asymptotes here happens to be the origin, happens to be 0, 0. It will not always be 0, 0, as we saw in our example over there. It actually translated and shifted down to -6, -1. But this description is a comparison of these two functions. Other things that a person might write, they both have two branches. Something like that. There are two blue branches because each separate piece is considered a branch. Anything that you see that you can tell me about could go in a comparison. And that's the basics of both inverse variation and how to translate inverse variation. And you're good. Good luck on your work, guys.